Hello, and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI-generated, and this video is supported by the Norwegian Research Infrastructure Service. NRIS is collaboration between Sigma 2 and the universities of Bergen, Oslo, Tromsø, and NTNU to provide national supercomputing and data storage services. These services are operated by NRIS and coordinated and managed by Sigma 2. In this video, we will continue to explore the new Olivia Linux cluster using the Cray module system. In videos 41 and 42, we performed matrix multiplication using a triple nested loop with OpenMP for parallel computing. In this video, we will use the Math Kernel Library, MKL, to perform matrix multiplication, again leveraging OpenMP for parallel computing. In video 41, I reviewed information about the new Olivia Linux cluster available on the Sigma 2 documentation pages, so I will not repeat that in this video. I am already logged into Olivia and currently inside the MXM OpenMP folder. Let me list the contents of this folder in the terminal. I have created a Fortran program that uses a routine from the Math Kernel Library, MKL, to perform matrix multiplication. Let's open this program using the Emacs editor. I am using a matrix dimension of 32, 7, 68. The first loop in the program initializes the matrices. Note that initializing the matrix C with zeros is unnecessary when using the MKL routine for matrix multiplication. The matrix multiplication is performed using the MKL routine dgem. We previously discussed MKL and how to use this routine in video 31, where we worked with MKL on the Fram Linux cluster. After reviewing the code, I exit the Emacs editor by pressing Ctrl-X followed by Ctrl-C to return to the terminal. We will now examine the job script used to execute the MKL Fortran program. The script is largely similar to the job script discussed in video 41. The key difference is that I will be using the Math Kernel Library, MKL, requiring me to load the Cray scientific libraries, which include MKL. The script compiles the Fortran program using the Cray Fortran compiler with only the FOpenMP and O3 options. Unlike the Intel compiler on Fram and Betzy, which required the march or xhost options, the Cray compiler automatically applies CPU-specific optimizations through loading of the AMD Turin module, which was done above. Additionally, the compiler options needed to use MKL with the Intel compiler on Fram and Betzy are unnecessary with the Cray compiler, as this is handled by loading the Cray scientific libraries, which was done above. After exiting the job script and returning to the terminal, I can clear the terminal. I am executing the Fortran program by submitting the job script to the Slurm queue system using the sbatch command. We can see that the job is assigned the number 3744. When I check the Slurm queue with the sq command, we can see that the job has finished. Before reviewing the results, I will clear the terminal. I will first list the folder contents, where we can see a job output file. Using the more command, I will open the Slurm job output file. The job output file begins by displaying the list of modules used by the job, and the list is generated by the module list command in the job script. The job output file shows some error messages, with the key issue being the phrase "relocation truncated to fit." This problem can be resolved, as we did in video 42, by using allocatable matrices in the Fortran program. Further down in the job output file, we can see that the job failed. Before making the necessary changes to the Fortran program, I will clear the terminal. I will first list the contents of the folder in the terminal before opening the Fortran program. The matrix dimension will remain the same as before. As in video 42, I will switch to using allocatable matrices. Before exiting the Emacs editor, I will save these changes to the program. Once back in the terminal, I will clear it again before executing the updated Fortran program with allocatable matrices. I am executing the new Fortran program by submitting the job script to the Slurm queue system using the sbatch command. We can see that the job is assigned the number 3746. When I check the Slurm queue with the sq command, we can see that the job has finished. Before reviewing the results, I will clear the terminal. I will first list the folder contents, where we can see another job output file. Using the more command, I will open this file. The job output file begins by displaying the list of modules used by the job, and the list is generated by the module list command in the job script. The matrix multiplication using Cray MKL was completed in about 5 seconds using 256 CPU cores. This is a significant improvement compared to the 221 seconds achieved in video 42 when we modified the loop ordering of the Fortran do loops. This highlights the importance of using the Cray scientific libraries whenever possible. On Fram, the same matrix multiplication using MKL was completed in about 67 seconds on 32 cores. MKL required about 32 seconds on Betzy using 128 cores. This demonstrates that the Math Kernel Library delivers impressive performance on the Olivia Linux cluster when using the Cray module system, especially compared to its performance on Betzy and Fram. The job output file indicates that the CPU efficiency is about 80% on the 256 cores used. In video 42, the CPU efficiency was close to 100%, but the computation took around 221 seconds to complete. Here, I have completed the same computation in just 5 seconds, despite having only 80% CPU efficiency. This clearly illustrates that even with 100% CPU efficiency, one cannot assume that the computation is being performed using the most efficient method. In video 42, we observed that the Fortran program with a matrix dimension of 32768 had a memory usage of about 25 gigabytes. The same memory usage was observed on Betzy and Fram when using the MKL routine for matrix multiplication. It is surprising that the Fortran program using the MKL routine included in the Cray scientific library shows a memory usage of about 44 gigabytes. The increase in memory usage from 25 to 44 when using MKL from the Cray scientific library is due to internal optimizations and temporary buffers utilized by the library to achieve high performance. This increased memory usage is a trade-off for better performance. The library uses additional memory for temporary buffers, data alignment, parallelism, and other optimizations that significantly accelerate matrix multiplication. In the next video, we will conduct a scaling analysis of OpenMP with MKL on Olivia. This involves measuring computation times with varying numbers of threads, starting from a single thread and scaling up to 256 threads. Scaling analysis in parallel computing is a method used to evaluate and understand how efficiently a parallel system performs as the number of processing units increases. It helps determine whether adding more computational resources improves performance and by how much. Scaling analysis is crucial for optimizing parallel systems and ensuring that resources are used effectively. I am looking forward to the next video. Wishing you all happy computing in the meantime.